Hello, I'm Professor Watson, and in this video, I wanted to do a little introduction to four of the classifiers that have been introduced so far in the course. We've gone into some depth on the first one of these, logistic regression. The other ones were introduced today, and they were introduced sort of as black boxes. So in an attempt to sort of unpack them a little bit, I'm going to introduce them now in a quick 1-minute introduction for each one. Later on in the class, we'll dive into each of these in more depth. We'll unpack them and really think through the intuitions of what's going on inside. But for now, I just want to give you kind of what the general idea is of using a classifier in this way. The first one, as I said, is logistic regression. Logistic regression is pretty familiar right now. Using a technique like linear regression, we can fit a parameter in logistic regression that corresponds to a crossing point in probability. This is on a sigmoid function. So we have a sigmoid function like this, which has a critical knee here in the curve, where values below this rapidly go to 0, values above this rapidly go to 1. And we can set a couple parameters in this sigmoid. We can set the gain of it, which is the slope here. We can have a very gentle transition from one to another. And we can set the probability, the threshold here, at which we convert from going very rapidly to 0 to going very rapidly to 1. This value here, this, which we can interpret as a probability of an event occurring, if we observe values that are above this threshold in our future sample, we're going to classify them as one category. And if we observe values that are below that threshold, we're going to classify them as another category. It is possible, if we have not really delved into it very much, to construct multinomial logistic regressions, where we're predicting multiple probability thresholds. And so we can have multiple categories that we can bin things into by linear regressing this point on this line. That said, we're not going to, we'll introduce those more when we're talking about multinomial classifiers. We've mostly covered this as a dual class classifier at this point. So that's logistic regression. You can take your data, you can use it to estimate the probability that you're in these different categories, and you can estimate the features, your input features. You can linearly regress your input features on that target value to draw a decision boundary that allows you to put some of your candidates in one class and some of the other. Okay. Logistic regression, very similar to the linear regression that we've done before, just for regressing on the probability of being in these classes. All right, so the second one of these is, let me label my axes here, reg. Okay, then over here we have a nearest neighbor, right? A k nearest neighbor is a classifier that is actually really easy to understand if you are in a low dimensional space. So imagine that we've taken images and we've projected them onto a couple of low dimensional components. Let's call this PCA1 and PCA2. So we've projected down onto a lower dimensional space. Obviously, you can do this in high dimensional space just fine. With k-nearest neighbor, you have a couple of labeled categories of data, right? All these are classifiers, they're all supervised, so you're going to have category labels. And what k-nearest neighbor is simply going to do is it's going to measure it when given a new data point like this one and ask, hey, what category does this one belong to? K-nearest neighbor is going to measure the distance, usually the Euclidean distance, to the nearest hey neighbors, and it's going to assign the value of this on the basis of what those neighbors. So if the closest, we have 3 neighbors here, one of them is red, 2 of them are blue. And so if we were having a k equals 3 nearest neighbor model here, we would call this new dot, oh, it must be blue because it's closest to these 2 blue ones, right? That's k nearest neighbor. It's a very straightforward classifier. Obviously, you can do this in higher dimensional spaces, and you can do this with different distance metrics. So this is Euclidean distance. You can use Manhattan distance or something like that. There are all kinds of distance metrics that you can use to do this. And you can choose your value of k. K is a hyperparameter in this that you pick at the beginning, and you should pick it on the basis of either something sensible, or you can do it on the basis of your data. So you can say, what k gives me the best classification performance in sample. And then as we did in this class, you can validate that on a held back out of sample set. You can cross-validate it on your data. So you can find values of k that are the best values of k based on what gives you the best performance on your data. All right. Third one of these classifiers, I'm going to try and draw a visualization for each one of them. Although for the multi-layer perceptron, this visualization metaphor will break down just a little bit. In a naive Bayes, we are using basically Bayes. So if you remember Bayes' theorem, you can say the probability of the posterior is, let's do this. Posterior is the prior times the likelihood divided by base rate or the So the probability that you observe some event given some evidence is equal to the probability that you observe the evidence given some event times the probability you observe the event divided by the probability that you observe the evidence. So that's one step of Bayes' theorem. You can see how you could use that to estimate a probability. What the naive Bayes classifier does is it attempts to estimate the probability of it is a maximum likelihood estimator, like logistic regression. So it's trying to maximize the likelihood of a particular, is trying to maximum the likelihood, but trying to find the set of parameters that maximize the likelihood of the model of the data, given the evidence that you have. So you can take all of the observations that you have every time you observe another data point, you are essentially getting a new piece of evidence, and the conditional probabilities of all of those pieces of evidence, you could plug into Bayes' theorem to figure out what the appropriate, the likelihood of observing this chain of events was. One of the ways that I visualize this is that I say, okay, imagine you have an unknown distribution. So you have you assume that the data points are being drawn from some unknown distribution, and you don't know what shape that distribution is. Well, every time you get a data point, you can take this existing distribution. We usually use a distribution we often use a prior distribution that is either something that we know. So if we were going to use if we had reason to believe that the data was Gaussian, we might use a Gaussian prior or something like that. We can also use what's called an uninformative prior. So like an infinitely flat, infinitely wide, zero probability distribution. To kind of like imagine infinitely wide, continuous, uniform distribution. And so that would be an uninformative prior. So we start with a prior like that. And then with each data point, we update the shape of the prior to match the shape of the data that we have. So as we'll do additional observations, which we can think of as these continuous probabilities, we get this tighter and tighter estimate of the shape of our data. Maybe it has a tail, maybe observe a point out here and a tail, something like that. And so as we do these updating steps, we get a better estimate of where the mean of our distribution is. Right? So that is, if we're looking at continuous value, we can update Bayes like that. We may also have bins. So we may also discretize this and say, okay, the presence of, we're going to classify this new data point on the basis of which of these bins of our discrete distribution, a Bayesian distribution, it falls into. And so this is a way of getting a classifier out of using something like Bayes' theorem to just classify what a discrete bin of probability that the point is. And the last one, which is the multilayer perceptron, here's where I'm going to have to change my visualization. This is a neural network model. We have a vector of data points that are our input. We have a weight matrix, which is a matrix connecting all of those input weights to a hidden layer. We have another weight matrix. We usually call this WIH. We have another matrix, WHO, which connects all of the hidden layer to an output layer. And given an input, we can have an output layer that has the different categories as things. And this is why we did one-hot transformations of our data, of our input data. So you might have, if you were going to do MNIST, your inputs would be a field of pixels, right, for your data model, your handwritten digits. And then you want to find a weight transform that you can multiply them by that will give you these hidden variables that when multiplied by this other weight transform will, light up this first unit when there's a handwritten 1, the second one when there's a handwritten 2, and so on, right? So you can use a neural network in this way as a classifier, right? So you can use logistic regression as a classifier. You can use nearest neighbors as a nice nonlinear classifier. You can use Bayes' theorem to classify data points, and you can use multilayer perception and neural network to be a classifier. They're all just a matter of kind of how you set up your input and output relations to employ these different algorithms to do your classification. So those are the classifiers that we've learned so far. We're going to spend a lot more time on each of these. We're going to, in our next lesson, we have maximum likelihood estimators. We'll talk about naive Bayes, how you construct the maximum likelihood estimator for a Bayesian distribution over a set of data points. We are going to do neural networks after that. We'll talk in some depth about how multilayer perceptrons work and how you compute the parameters of these. So we're going to deep dive into these slower. They're going to get reinforced over multiple levels. But for now, this is kind of how you think about them. This is kind of what I would like for you to have in your brain when you think about these different classifiers. Okay, great. I will see you back here in future.